Hello friends, welcome to LI Learn. Today in partial differential equations, we will study the Lagrange's method to calculate the general integral or general solution of a quasi-linear first order partial differential equation. So friends, आज हम क्वासी-लीनियर फर्स्ट ऑर्डर पार्शियल डिफरेंशियल इक्वेशन का जनरल इंटीग्रल कैलकुलेट करेंगे यूजिंग Lagrange's method. So friends, now what is our quasi-linear PDE? We have discussed in our previous videos, that was classification of partial differential equation, and even the general integral we have discussed in our previous videos. Okay, so for the definition of general integral or the general solution, you can visit our previous video, that was types of solution, and for the definition of quasi-linear first order PDE, visit our previous video, that was regarding classification of PDE. Okay students, so with the knowledge of these two things, we start with the Lagrange's method. Now friends, this theorem gives us the Lagrange's method for calculating the general solution of quasi-linear first order PDE. So the solution of a quasi-linear first order PDE, which is of this form. Okay, this was the basic form of the quasi-linear first order PDE. Okay, so the general solution of this PDE is of the form f of phi psi equals 0. So students, here this function f is an arbitrary function and these phi and psi are two known functions. Okay, so we'll just tell you what are these phi and psi. So again, this f is an arbitrary function and phi and psi are solution curves of the characteristic equations or subsidiary equations given by these. Now friends, these equations, they are called characteristic or subsidiary equations. These equations are used to calculate the general integral of this first order quasi-linear partial differential equation. So friends, just see that this a over here is nothing but the coefficient of this ux. Okay, this a and this a that you are seeing over here, they are same. Similarly, this b is the coefficient of uy. Okay, this b of xu xyu is this b. Okay, and similarly this c is over here. Okay, this c and that c, they are same. So this is how we obtain these set of equations, and these set of equations are called the characteristic equations or subsidiary equations. Okay friends, so in order to calculate the general solution of this quasi-linear PDE, what we do, these subsidiary equations are also called Lagrange subsidiary equations. So we consider these equations and we calculate two solutions of these equations, which are named phi and psi, and then any arbitrary function of phi and psi will give us the general integral of this quasi-linear PDE. So friends, I again repeat that in order to calculate the general solution of this first order quasi-linear PDE, first of all we calculate these subsidiary equations. Okay, and then we find two solutions of these equations, which are named phi and psi, and then any arbitrary function of phi and psi when equated to 0, this will be the general solution of this first order quasi-linear partial differential equation. Okay friends, and further the functions phi and psi that we obtained as solutions of these characteristic equations, they are called the solution curves. Okay, this phi and psi, they are the solution curves of this equation. Okay, this phi equals to C1 and psi equals to C2. So friends, the solution curves given by phi equals to C1 and psi equals to C2 are also termed as families of characteristic curves of 1. 1 is this equation, the initial equation of which is the quasi-linear PDE. Okay, so phi and psi are also called the families of characteristic curves of this given initial first order quasi-linear PDE. Okay friends, so for this initial first order quasi-linear PDE, first of all we calculate these subsidiary equations, then we find two solutions, phi is equal to C1 and psi equal to C2 of these equations, and then we take an arbitrary function of phi and psi, and this will be the general integral of this first order quasi-linear PDE, and the solution curves phi and psi are also called the family of characteristic curves of this initial partial differential equation. Fine friends, so this was the theorem that explains us the method of calculating the general solution of a quasi-linear first order partial differential equation. Now friends, the first order quasi-linear PDE can be given to you in this form: a of xyu into ux plus b of xyu into uy equals c of xyu. Here u is the dependent variable and x and y are independent variables, and u is the partial derivative with respect to x, and uy is the partial derivative of u with respect to y. Now this first order PDE can also be written in this form. Okay, sometimes in the question instead of this form you may be given the first order quasi-linear PDE in this form. The difference is that instead of the dependent variable u, we have changed it to z. In this equation, z is the dependent variable. So accordingly, instead of ux, we have zx. Instead of uy, we have zy. Okay, and the equation can also be given in this form, that is, the coefficient of zx may be written in this form. We are just like changing the naming. Okay, the names might be in this form. In the questions, the format of the partial differential equations that is given to you can be in any of these forms. And finally, it can be expressed in this form also. As you know that p is the partial derivative with respect to x, q is the partial derivative with respect to y. Okay friends, so these are the four types in which the first order quasi-linear PDE may be given to you. Okay, all these means the same, just like a way of writing. Fine. And now it has one more short form, like instead of writing x, y and z, we can also write simply in this form. What we have done over here, that instead of writing capital P as a function of x, y and z, we are simply writing it as P and capital Q. Okay, so this basically means that the first order quasi-linear PDE may be given to you in any of the above 5 forms. Okay, so like if you're given unknown form, don't get confused. Okay, they all mean the same thing, and mostly the questions that you will be dealing with will be given in any of these forms only. No other form is usually used. Okay, so just try to remember all these forms. So now with this knowledge, now let's move on to our Lagrange's method. Lagrange's method. So as I already told you, that Lagrange's method is used to find the general solution of a first order quasi-linear PDE. Okay friends, so let's begin with it. Method 1. Now Lagrange's method, so it can be used in 3 to 4 ways. Okay, firstly we'll explain the first way. So first of all, let this be my first order quasi-linear PDE. Okay, so I have taken it to be of this type, P into Zx plus Q into Zy. So friends, just make a mark over here that this is not B, this is Q. Okay, just like instead of B, make it Q. So my quasi-linear PDE is given in this form, P into Zx plus Q into Zy equals R. So this is my first order quasi-linear PDE. Now I move towards calculating its general solution. So friends, the first step is to calculate the Lagrange subsidiary or characteristic equations. Okay, firstly form the Lagrange's characteristic or Lagrange subsidiary equations. And the equations that we have already seen in the previous theorem are of this type. Dx over P equals dy over Q equals dz over R. Now this P is nothing but the coefficient of Zx. Okay, just this P is moved over to here, and this Q is nothing but the coefficient of Zy. Again, this is not B, this is Q. So this coefficient of Zy is Q, which is put over here, and this R is the function of x, y and z, which is on the right hand side of the equation. Okay, always remember that this R is on the right hand side of the equation. So firstly, when you are given the first order quasi-linear PDE, first step is to form these Lagrange subsidiary equations. And then the second step, as I already told you in the previous theorem, is to calculate two solutions phi and psi of these Lagrange equations. Okay, so friends, step 2 is to find two linearly independent solutions phi and psi of above subsidiary equations. Okay, so the solutions that we'll be calculating phi and psi, they will be linearly independent. Okay, the method that we'll be using will ensure that the two functions are linearly independent. Okay friends, so these were the two steps. Now we will move towards how to find the two solutions phi and psi of these Lagrange equations. So firstly, in this method we'll be using comparing ratios. Okay, so you must be remembering that the Lagrange's equation are given in terms of ratios, that is dx over p equals dy over q equals dz over r. Now these were your Lagrange subsidiary equations. It is given in terms of three ratios. Okay, so comparing ratios means we'll be using two of these ratios. Okay, so suppose we are comparing the first and second ratio. So initially we compare the first and second ratio, and we get dx over p equals dy over q. So what we did over here, we are comparing the first two ratios of the Lagrange subsidiary equations. Next, what we do, we just cross multiply and get q dx equals p dy, and then we get this equation q dx minus p dy equals 0. Now what we do further, we solve this equation furthermore and get the solution phi. Okay, and for the next solution we compare the other ratios. Suppose we are comparing the other ratio as second and third ratio. Okay, so as you remember, the second and third ratios are these: dy by q equals dz by dr. Now this was my third pair of ratio. So again, after comparing, we cross multiply r dy equals q dz, and then we write it in this form. Again, we solve it further to get a solution. Fine. And lastly, what we do, we compare our first and third ratio. So lastly we compare the first and the third ratios. That was dx over p equals dz over r. Okay friends, so I'll just for your remembering, I'll just write over here that my Lagrange subsidiary equations was given in this form: dx over p equals dy over q equals dz over r. Okay, now what we are doing, we are comparing the first and the third ratio. These two ratios we are comparing. And again, as done before, we cross multiply rdx equals pdz, then we write it in this form: rdx minus pdz equals 0, and then we further solve it to get a solution curve. Fine friends, so what is the second step? To find two solutions phi and psi of the Lagrange subsidiary equations by comparing ratios. So these are the three types of comparison that we have to do. Now friends, depending on questions, we will be selecting which ratio to compare. What we have to do, we have to compare any two sets of ratios. I showed comparison of three sets of ratio, but when we are solving a question, we have to select two sets of ratios. And it will depend on questions to question which questions will give us solution curves easily and faster. Accordingly, we will select which set of ratios we have to compare. Okay, so I repeat, we have to compare two sets of ratios, and on comparing, we will get two solution curves. Firstly, phi is equal to C1, and secondly, psi is equal to C2. Now these two solutions are obtained by comparing the two sets of ratios. Suppose phi is equal to C1 is obtained on comparing first set of ratio, and psi is equal to C2 is obtained on comparing the second set of ratios. Fine friends, so we compare two sets of ratio and we get the two solution curves as phi is equal to C1 and psi equals to C2. Now, one more point I want to make over here is that it might be possible that on comparing the third set of ratio, we will also get a solution, but that solution will be depending on the first two solutions. Means we cannot get three independent solutions. If we are calculating the third solution, that will be depending on the first two solutions. Okay, so on comparing the set of ratios, we can get only two linearly independent solutions. Fine. So you select any two ratios and compare and get two solutions. You need not calculate the third one. If you calculate, it will be depending on the first two. Okay friends. So phi and psi that we calculate will be linearly independent. So this was my step 2. Now let's move on to step 3. Step 3 is that the general solution of given PDE is of this type: f of phi psi equals 0, where phi is the function we obtained by comparing the ratios of the Lagrange subsidiary equation, and psi is the function that we obtained by comparing the second set of ratios of the Lagrange subsidiary equations. And this f is an arbitrary function. Okay, so again I repeat what we have to do. We have to first of all write the Lagrange subsidiary equations. Secondly, compare ratios and get the two solutions phi and psi, and then the general solution will be an arbitrary function f of phi and psi. So this will be my general solution of the first order quasi-linear partial differential equation. So friends, again I repeat that in order to calculate the general integral or general solution of a first order PDE given in this form, what we do, first of all we calculate the Lagrange subsidiary equations. They are in the form of these three ratios. Okay, then what we do, we select one set of ratios, say this one, and obtain a solution, say phi is equal to C1. Then we select another set of relation, say this one, and obtain a solution, say psi equals to C2. And then what we do, f of phi psi equals 0. This is my general solution. Okay, here f is an arbitrary functions. Okay friends, so these were the steps regarding calculating the general integral of a first order quasi-linear PDE. Now we move towards a question. So my first question is, find general solution of first order linear PDE given by the equation xp plus yq equals z. Here this p is the partial derivative of z with respect to x, and this q is the partial derivative of z with respect to y. So now let's move towards calculating the general solution. Now friends, if you remember, the first step was writing the Lagrange subsidiary equation of the quasi-linear PDE. So let's try to write the Lagrange subsidiary equations. So Lagrange subsidiary equation, if you remember, are of the type dx over coefficient of p, which is this dx over x, equals dy over coefficient of q, which is y, equals dz over the function that is on the right hand side. Okay, so these are my Lagrange subsidiary equations. Again I repeat that if my quasi-linear PDE is given in this form, pp plus qq equals r, then the Lagrange subsidiary equations are dx over capital P equals dy over capital Q equals dz over capital R. This capital P is the coefficient of this partial derivative with respect to x, and this capital Q is the partial derivative, it is the coefficient of the partial derivative with respect to y, and this R is the term on the right hand side. Okay, so accordingly we have written our Lagrange subsidiary equations. Here the coefficient of this partial derivative with respect to x is only x, so we have written an x over here, and here the coefficient of the second partial derivative is y, so we have written y over here, and the term on the right hand side is z, so we have written z over here. So this is how we have written the Lagrange subsidiary equations. Okay friends, so after writing the Lagrange subsidiary equations, let's move on to our second step, that was comparing ratios. Fine. So first of all, we will be comparing the first two ratios over here. Okay, and then the other set of ratios. Fine. So we start with comparison of ratios. So first of all, we have taken the first set of ratios, that is dx over x equals dy over y. Fine. So now we have to solve this set of ratio in order to get our first solution, that is phi. Now friends, here this is a very simple expression. We don't need to do any calculations in order to solve it. We don't need to cross multiply and take in y over here or x in over here, because it is already in very simple form. What we have to do, we just integrate it on both these sides. Okay, so we'll integrate it, and then we will get, as you know, the integration of 1 over x with respect to dx is natural log x, and the integration of 1 over y with respect to dy is natural log y, and then you get an arbitrary constant. So this is what we get: natural log x plus natural log y plus a constant. This you got by integrating this term. Natural log y you got by integrating this term, and this is an arbitrary constant that you get upon indefinite integration. Okay, now friends, in order to just make it a little more simpler solution, what we do, we will write this constant function in terms of log. Now as you know, that natural log and the exponent function are the inverse functions to each other. So we can express this C1 in the form as follows: natural log e C1. This natural log and this exponent function are the inverse functions to each other. So on applying, they both cancel each other and we get only C1. So we can write C1 in this form. The intention of writing C1 in this form is that we want to express our solution in a more simpler manner. So what we can do now is that we can take this natural log y onto the other side. So we get natural log x minus natural log y equals natural log exponent C1. Now as you know that log of a minus b can be written as log of a over b. And the next thing is that our function log is 1 function. So if f of a equals f of b, where f is 1 we get a equals to b. So what we get over here is that x over y will be equals to e power c1. Okay, so that is what we get. X over y equals e power c1. So this is a very simple form of a solution. Now next, what we can write, we can express this constant in a simpler manner. Now e to the power c1 is a constant, and because c1 was a constant, so we can write this entire constant as a c2. Okay, so that is what we do next. X over y equals c dash 1. We can also write it as c2 or anything. So what we did over here, we wrote this constant in a simpler manner, that is c1 prime. Okay, so now this is my first solution that I obtained by comparing the first two ratios of the Lagrange subsidiary equations. And my first solution is phi equals x over y equals c1 prime. Now this is the first solution, phi. Now similarly, I will be calculating my second solution, psi. That I will be calculating by comparing another set of ratios. In this question, I will be using the second and the third ratio. Okay, so next I compare second and the third ratio, that is dy over y equals dz over z. Again, as in the previous case, these are very simple expressions. We don't need to calculate anymore in order to get a solution. We don't need to take z over here or y over there, because we can easily integrate both these sides and get our solutions. So what we do, we apply integration on both these sides to get the solution as natural log y equals natural log z plus a constant c2. Again, as before, we will express this c2 in this manner, natural log exponent of c2. Now we take natural log z over there and we get this expression, and again as in the previous case we write this as natural log y over z. And now because natural log is a 1 function, so what we get over here, that y over z equal e power c2. Okay, so what we get over here is that y over z equals exponent power c2. This we got because log is a 1 function. Now next we write e to the power c2 in a simpler manner, say c2 dash. We get y over z equals c2 dash. c2 is a constant, so exponent of c2 is again a constant, so we can express it in this form also. Okay friends, so now my second solution is psi equals y upon z equals c2 dash. So this is my second solution. Okay friends, so we have obtained our two solutions, phi and psi. Okay, so if you remember, my initial solution phi was x over y. Okay, and now I got psi as y over z. These are my two solutions obtained by comparing first two ratios and second and third ratio. Now friends, suppose if you are calculating another solution by comparing the first and third ratio, then you will get another solution, say capital Phi equals x over z. But this will be depending on the first two solutions, because we can write it as x over y equal, sorry, not equal, into y over z, which is nothing but phi into psi. So if we are trying to calculate one more solution by comparing the third set of ratio, then that solution will be depending on the first two solutions. So the three solutions will not be linearly independent. So only two solutions can be linearly independent. So when solving a question, just calculate two solutions by comparing any two sets of ratios. Fine. So after calculating the two solutions, you can write your general solution. So the general solution is as follows. The general solution is f of phi psi equals x over y, y over z equals 0. Now this x over y is the value of phi that we calculated, and this y over z is the value of psi. Okay, and this f is an arbitrary function. Fine. So now this is the general solution of the first order quasi-linear PDE that was given to us. Okay, so I hope you remember the steps. Firstly, we write the Lagrange subsidiary equation, then we calculate two solutions, phi and psi, of those Lagrange subsidiary equations, and they will turn out to be linearly independent. And after that, we write a function of phi and psi. This f is an arbitrary function, okay? So any arbitrary function of phi and psi will be the general solution of the given first order quasi-linear PDE. Okay friends, so with this we end today's lecture, and in the coming videos we will be discussing the second and third method of Lagrange's method. Okay, in the second and the third method, what we do, we try slightly different method of calculating the two functions phi and psi. The remaining steps will be same, only the way to calculate phi and psi will be slightly different because certain questions have different approaches. For that, those methods will be more useful. So for those methods, do visit our coming videos. So friends, thank you for visiting this video. For more videos, keep watching our site lilearn.com. Thank you.